All right, I think we're going to get started here. It's my pleasure to introduce Will Thompson. I've known Will for I think it's like 15 years now, and Will has been a close colleague and friend. We've interacted with them for a long time. I've known Will since they first started the proteomics resource at Duke, and there's a number of them that we've interacted with over the years, and this resource has become kind of, in my mind, a great model for kind of how a lot of cores could operate and should operate, and I think they've kind of taken an extra level of stringency to be able to be collaborative but practical, offering useful solutions for their investigators. It's a great, fantastic team of people. Just to let people know a little bit about Will. He actually trained with Jim Jorgensen at UNC, and so his background really is in chromatography. He's a chromatographer at heart who, went with a mass spectrometry detector, needed a detector. And he's often one of those people, if you have interesting chromatography problems, it's interesting to kind of chat with him and to bounce these off of. And then he worked very briefly at Glaxo, but then Glaxo decided they didn't want to have a proteomics group anymore. And then they moved. There were actually several of them that actually ultimately moved to Duke. And I think it's been a great thing for the scientific community in general, although at the time it may have not seemed so great as a decision. But anyway, Will's also a fantastic teacher. He is able to present these very complicated topics in a straightforward way. And one of the things I think he's taken on more of the effort in is, you notice they've now become the proteomics and metabolomics shared resource. And I think Will has taken on a lot of the lead of that aspect. One of the things, he was very much an early adopter in trying to use Skyline to support this metabolomics resource. We've been very kind of clear in just calling it small molecules because people aren't really sure what should we call it. It's basically non-peptides. That's basically what these capabilities are. And at the same time, he's been great in being able to help us and provide some sort of information to kind of share with people, because we want people to know that you can use Skyline for all molecules, not just.
Right. Thank you. Yeah, very, very kind introduction. So my goal, since only 2 people raised their hand yesterday, is for everyone, maybe let's say 85% of the people, to still be awake at the end of the next 2 hours. So I try to set the bar low, and then we'll be successful. So in reality, though, what my goal is, there's a tremendous team. So Brian Pratt in the back of the room. Everybody who's interested in small molecules should know Brian. Even if you're not interested in small molecules, you should still know Brian. He's a great guy, likes to do a lot of hiking, and has been a key member of the team here that's been developing small molecule content. As with everyone on the Skyline team, you send Brian an email, you get something back right away. You ask for, does it do this? And he's like, no, but it will next week. Features really appear kind of in incredible speed. And are just tremendously well implemented. So what I really want to share with you in the next maybe couple of hours is some ways which you might use Skyline, even if you're in a peptide lab, for starting to do small molecules. If you're like me, you started off doing proteomics, and then eventually, if you do it long enough, somebody will come to you and they'll ask you a question that's a small molecule application. And because you've got an LC and you've got a mass spectrometer, technically you're able to answer those questions, right? And so eventually, after you say no long enough, you'll say yes. And at that point, I hope that you'll give Skyline a try for small molecules. Just the fact that you're sitting in this room tells me that you're already a good candidate for that. At that time, you may need to kind of retrain yourself if you've not used what we're going to do today in a while. So currently, Brian and I have worked together to put content together for 4 small molecule tutorials, which are on the website. So if you look on the right-hand side under navigation under tutorials, there are currently 4 of them. The three that are longer are actually a lot newer. One of them was put together very early on in small molecule land for Skyline, but the later three kind of cover some method development, how you might do things like collision energy optimization, retention time, scheduling, those kind of things in a small molecule environment. Quantification in a small molecule environment, which is something we're going to do today because I know you haven't seen in Skyline yet how Skyline kind of handles quantification. So what I mean by that is calibration curves, internal standard ratio into calibration curves, weighting, quantitative fitting of calibration curves. So that material looks very much the same in small molecule world as it does in peptide world. And you're going to hear from Andy Hufnagel tomorrow morning. He's going to just jump right into doing, targeted, what we would call, calibrated quantification. And so by doing this afternoon, hopefully that'll put you in the frame of mind for that content. You'll have seen it already. And just keep in mind, if you're just doing this for small molecules this afternoon, it looks very, very much the same, and all the settings are very similar for peptides. And then there's one that we added kind of at the end of our cycle for small molecules, which is how to look at high resolution data. So a lot of times people will collect data from metabolomics using high resolution, and they may use some other tool like XCMS or Progenesis or another kind of tool to do differential measurements on the precursor intensities. We found that Skyline is really useful once you have that differential measurement for doing a secondary software validation, where you might take those targets which were, given as statistically significant and put them into Skyline and then extract that data and do another statistical test on them just to verify that the software first didn't make a mistake. The software you used to collect the original data didn't make a mistake. And we use this in the proteomics context too. Maybe we've not used just Skyline. Forgive me for saying that, but maybe we've not used just Skyline for all of our high resolution data, discovery data analysis. But we'll take those same peptides that are of interest now, put them in Skyline, and verify that what our other software package gave us, gives us the same answer in Skyline. So kind of how to do that is set up in this high resolution metabolomics tutorial. Do we have any other plans for other tutorials, Brian? Maybe one on library, spectral libraries will be. We haven't talked about it anymore, but that's definitely one that we could potentially do. Kind of how to do. But if there's any other ideas for when you're kind of going through small molecule content and you're like, this doesn't really describe how to do X, Y, Z. Be sure and let either me or Brian or someone on Brendan know, and we'll consider putting together or maybe if you've got a really good example, we'll ask you to help draft it. Okay, so let's launch right into what Skyline can do and its motivation, at least from some of the users' perspective. Andy Hufnagel, 5 years ago actually, put up a slide very similar to this at the user meeting, and said that Skyline just makes a lot of sense. It's inherently intuitive for small molecule analysis, and these are the reasons why, right? It is you can have a target list with easy addition of MRM transitions, molecular formulas, and molecular adducts. Now that initially wasn't very easy to do, but I'll show you kind of how Andy and a couple other groups did it initially. But the fact that they were able to go through that headache of adding these things, basically tricking the software in order to do it, even when it only did peptides, shows you how motivated they were to make Skyline work for small molecules. And those reasons were really because it's easy to manipulate large data sets. It does a nice job of chromatographic alignment between samples and reliable peak picking, automated peak integration. It has a very flexible and simple report configuration, which you'll see more about later in the week. Quantification using standard curves or stable isotope dilution is built into the software, and data export for analysis outside of Skyline is quite easy. So they were so motivated to do this that the first implementation was a hack, and I realized you can. I should have said that these slides are all available on the. So if you have trouble seeing the screen, they're available on the user participant page. So
people are looking at it.
yeah, great, good, yeah. So I'm going to point at like a blurry screen up here, and you just look down in that general location. Okay, so what Andy did, which was and his group did, which was pretty impressive, was actually they modified individual amino acids with post-translational modifications, and they made a tremendous number of post-translational modifications. It's such that they could add the PTM, right, the new fake PTM, to a peptide or to an amino acid, and then that would then have the weight of a lipid, right? And then what they said is, oh, well, every acylcarnitine and sphingomyelin and lysolipid, lyso-PC, fragments to give the same product ion as 184.1. So they made one of the new amino acids have a weight of 184.1. So when you generated the Y1 ion, it gave a product ion of 184.1, right? And yet the other amino acid that was in there was balanced, so that the total was the sum of the molecular weight, right? So tremendous amount of work just tricking Skyline into saying, and I was like really happy when he did this, because this was what really showed Mike how powerful Skyline was. At least I've heard that's the way, you've heard the stories, like eventually if they've hacked things long enough, you'll be convinced that
if someone wants to use it this badly, then we should probably get it easier.
So, and it turns out that Andy was not the only one. There's a group that published this in JPR in 2016. So even 3 years later, there's a publication accepted in the JPR that basically showed how to do this, how to hack Skyline. I mean, the title should have been "How to Hack Skyline to Do Small Molecule Analysis," and it worked. It absolutely worked. By this time, by the time that this was going, the group here was well on the way to implementing Skyline for metabolomics. So in our laboratory, the way that a project might go is usually something like this. We'll meet, we'll have a consultation, a study design. We'll select a platform that we already have, or we'll understand why one of the platforms we have may not work for that project. If we can select a platform we already have, which is what we hope, then we'll kind of move forward towards sample prep and data collection, data reporting and follow-up meeting, and then the publication of results. And so where I've got the little Skyline or panorama diagrams is where in our workflows that we use Skyline. The projects that I really enjoy are projects where we don't really have a platform that meets the collaborators' needs, and so what we have to do is go and define what kind of figures of merit. Does it need to be calibrated quantitation, or can it be differential? How many analytes do you need to measure? Do we need to know stability of them? How kind of rigorous on the quantitation do we need to be? We'll do a literature review. We'll then get standards. Nice thing about small molecule quantitation is you don't have to synthesize 765 proteins in order to then characterize them. Most of the time, you can order standards, and then we do potentially, then we use Skyline heavily in the method development cycle for looking at extraction, calibration, what we would call a mini validation. For context, most of the work that our lab is doing is not in a GLP. We're not a regulated environment, but we have a lot of experience in that world. So we do things what we would call in the spirit of GLP. So when we're doing calibration, we'll do calibration curves beginning and the end of a plate. We'll do quality control samples, known, unknowns, low, mid, and high, 3 levels at 3 times during the context of a plate. So we kind of build these, we do validation, intraday CV validation on the assay. So a lot of those things are kind of built into our design method development pipeline, but we are not a GLP, we're not a regulated lab. Any questions about kind of where Skyline might fit into, or comments about places it might fit into kind of the workflow? Because this is, all right. Why would you want to be this rigorous with small molecules? I think there's a lot of as we all, I think, are probably aware as scientists, there's analytical science has been under fire for being irreproducible, I think, in a lot of different areas. And mass spectrometry is no different, right? And so one of the key things we can do with Skyline and with small molecule tools that we build is show that we're being reproducible. And the same answer is given from our assays day in and day out. So this is just an example of a Golden West serum standard. So this company Golden West sells different biological matrices that you can buy. And this particular standard was analyzed over 100 times during the course of about 7,000 sample analysis. This particular plasma sample is prepared on every plate of every assay of every study that we do in our laboratory for small molecules, okay? And it may not be a plasma study. We still have this one sample we prepared every time. And the reason is because we can tell whether or not the preparation or the analysis or something went awry by comparing the data from that sample to all the longitudinal data that we have. So this is just an example of the assay we use for amino acids and biogenic amines, and then the average variance as a function of time over the course of about almost 3 years. I need to update this slide because we've got another almost 2 years worth of data, but this kind of proves the point, I think. And the nice thing is if you have a study that goes south, you can go back to your investigator and say, okay, we know that the assay was performing well, maybe something about the samples. Anybody ever have something we call an analytical success and a biological failure? Does that happen? Anybody know what I'm referring to there? Where the analytical data looks awesome, but the investigator doesn't find any difference in the thing that they expect to see different, right? That's an analytical success and a biological failure. And depending on your workflow, and you may be able to show that it was actually analytically solid, or you may have this open question about whether or not the experiment failed for analytical reasons or biological reasons. So my goal as the person who's taking the samples and making the quantitative measurement is to try and as much as I absolutely can, show that it was not an analytical failure of the experiment, right? At least eliminate that, right? A lot of times we're blinded to the studies, the sample sets initially. We don't know what groups they belong to, right? So the only thing we can measure is quality control and outlier. We can measure outliers, but we wouldn't know why they were an outlier, for instance, right? So this kind of data helps us to understand that. How we do that, and I kind of call this a little bit tongue-in-cheek future-proofing metabolomics. You can put proteomics in this slide because I think once you get a protein assay to a certain targeted sort of stable assay set, like Mike was talking about yesterday with the sort of, or was it this morning with respect to the sort of once you've validated an assay to a certain point, you want to start building in calibration curves beginning and end of your study, analytical quality controls, which are a couple of different types of quality controls. One is a study pool. So how many people utilize a study pool or know what a study pool is? So how do you go about making, what does that mean to you? What do you? Yeah, so why is that important? Well, can you tell kind of the crew, because there's like 3 or 4 of you guys that are doing it. How do you use that?
So I'm using the past like TMT sets or cross sets.
Yeah, so you got multiple TMT experiments you can normalize between. Okay. Have you used it in any other types of experiment not TMT?
We've done it in like functional assays, but it wasn't the samples. It was like, oh, we got a plasma from the lab.
Do you have an IRB for that? I'm just going to answer that question. No. So you have a pooled sample, right, that you're going to measure. Typically, it is exactly what you were saying, which is you have a group of samples and then that you're going to analyze, and it's a little bit of all of those samples that are being analyzed together. Anybody else? A couple other hands that we're using. How do you guys use the study pool?
We use every sample that we use to integrate file.
Okay.
Usually that helps us to see the digitization for all the variables.
So So you'll run it, but you'll run it before you run your sample set, just to know if the quality of the digestion and everything went appropriately.
We do use, but we do matrix it between as well.
Okay.
It is more to compare like day-to-day variability as well.
Okay. Yeah. So you can, in this context, there are a couple of ways that we use this. One is to test at the very beginning of a study whether or not you think that the sample prep went well. The second is to know whether or not the average, say you got a targeted assay for 150 metabolites, right? And you've got a calibration range, right? If you want to know what the biological average of all of your samples is, you can measure that one sample, and you at least know whether your study average is going to be way up the top of the curve, way at the bottom of the curve, or somewhere in the middle, right? You hope that it's somewhere where the study average is going to be well calibrated, right? That's one sample you can measure. The other thing you can do is measure it multiple times within a day or within a plate, right? And then put that same pool on the next plate, prepare it again, right? And that way you have something to normalize between days. That's like the TMT example where if you've got different plates, that can help you to reduce batch effects. Even if an assay is quantitative and calibrated, there will be slight day-to-day effects. It's impossible to avoid the temperature of the room during your sample prep, the amount of oxidation. I mean, there's just variability that's inherent. If the biological effect is small enough, you'll see the day-to-day effect no matter what the assay is, okay? The other thing is that if you have that pool run, you can actually use the variability. So if you have the pool, and then you have all of the individual sample measurements, right? If you take the mathematical average of all the samples, right, what should it be equal to? The pool, right? So if it's not equal to the pool, what does that mean? If the mathematical average of all your samples is not equivalent to the pool, what does that mean? I mean, it should be, right? You took a little bit of every one. It's by default an average, right? What does it mean if it's different? If it's higher or lower than
The pool is wrong.
It's not that the pool is wrong. It means if it's higher, right? If the average of all the samples is higher, the only way that the pool could be higher than the average of all the samples is that the samples that you measured at the high end weren't high enough to push that average up, right? So that means you got suppression at the high end, that you're not linear in the calibration range at the high end, right? If the pool is measured lower or higher than the average, right, then the opposite is effect. It means you've got saturation at the low end of the calibration. So if you calculate bias, basically difference between your pool and the average of all of them, right? And by the way, you don't have to have this for absolute. It doesn't have to be absolute quantitation. If you just take peak intensities, right, and you average all the peak intensities, and you average and you know the peak intensity of the pool, you can still tell whether or not you're in the linear range of the assay for that peptide. Whether or not all the samples are in the linear range, right? So there's multiple ways you can use this pool, and we try. I apologize for taking 5 minutes to talk about that, but I think everybody should be implementing, whether or not you're doing proteomics or metabolomics, always make a pool and analyze that pool in the context of your study. Other things that we do are these global reference pools, which I already mentioned. Depending on the study, we might pull the NIST, the very, very expensive NIST reference material, analyze that. Why that is useful is because for a lot of metabolites for this NIST SRM 1950, there are known quantitative values. So you can tell whether or not your assay is giving the right number, right? Because there are, values established for that sample, right? And if the values are slightly off for your assay, then that just helps you to calibrate the number up or down, right? A little bit. A lot of times you can just recalibrate your assay to this NIST material. If you're analyzing an analyte which is not established in there, then you can report your value in your publication, right? And then anyone else who analyzes their metabolite using any other method, their favorite method, because we're analytical scientists and we like to tinker. So I want to come up with an assay that's more sensitive or more, faster or just better than yours, right? Then I can compare my data, right, to your data by looking at the value that we both got for NIST SRM. And I've done this a couple of times in the context of reviewing papers and say this is a great experiment. This is a fantastic new method, but I'd like you to report the value you get for your method, right, for some reference materials. So when I'm trying to implement your method, I know whether or not I get the same number, right? It just kind of helps helps the community to move along, right, to translate better. And then the low, mid, and high QC standards are typically known unknown. So you make them from the same calibration reference material you're using, but you know what the result should be, right? Typically low, mid, and high level in your calibration curve, but you treat them as unknowns, right? And you calculate how closely you got to the right answer in the end. Okay, so those are low, mid, and high, and those go in the same. So if you're doing math at home, in order to run 76 samples, we typically do about 130 injections. Is it necessary in this context to do technical replicates of your samples? Should we be doing technical replicates of our samples? Not really, right? We're not using reproducibility of any one sample, right, to determine quality. We're measuring each sample once, right? And then we're using all of these other these quality metrics, right, to determine quality of our data set. This way, we're not, if somebody wants to give us randomized blinded samples, we had a cohort of nearly 1,000 samples, and they picked 20 samples randomly, and they just duplicated them, just blinded to us. They said, okay, we're going to put these samples in there twice. And we're like, fine, like you can do that all you want to, doesn't bother me, because I'm going to know the quality of my study without knowing what samples are duplicated, right? We're not required to know that information. Okay. So this is just a quick example of a scenario, and I like to put this out there because a lot of people think, okay, what is the scenario when I might want to do small molecule quantitation in Skyline, and how is it going to help me? So we were approached by a group at Duke that basically had this discovery a fairly long time ago that a high cholesterol diet caused an increased tumor burden in this breast cancer tumor model, and then they discovered through other techniques, RNA-seq and others, that there was sort of metastatic effects of this cholesterol diet were actually caused or required the CYP27A1 enzyme, which is the enzyme that converts cholesterol to 27-hydroxycholesterol. They then showed that inhibition of CYP27A1 decreased metastasis, so the story is getting stronger. They can add a small molecule drug, and inhibiting that enzyme decreases the tumor burden. When they came to us, they were at the situation where they said, okay, the reviewers have said this is all great, but what you haven't done is shown anything about the actual levels of 27-HC and how that's affecting you. If you think this is causing these effects, then you have to measure those compounds, okay? And so our job was to basically develop an assay which could be done from 50 microliters or maybe slightly less, or 50 milligrams of tissue to measure all these isoforms of hydroxycholesterol, and then show, in the end that the differences in the actual amount of 27 hydroxycholesterol are different. So that's what we like to do. And then the way our lab works is that we then take that assay, we put it on the website, we market it to everyone. Hopefully more people, we go through the effort of developing an assay, then we try to, sell it, for lack of a better word, to lots of investigators. So you just learned a lot about system suitability, so I'm not going to sort of belabor this point, but we have a lot of information here that is also relevant to small molecules. An example of this is that we might have a 1 microliter solution at 1 micromolar of 27 hydroxycholesterol. In this case, we use the D6 because we can just put it, we know it doesn't have any interference based on what was there previously. We can analyze it as a function of time and look at peak area here, as a function of time, chromatographic completion time. Over time, clearly we had a problem with our chromatographic setup here, and then made a correction and got back. We keep good data and bad data in our system suitability documents because it's important to know what bad data looks like, right? So you want to flag them and apologize if Lindsay showed that, but in AutoQC and in Panorama, you can annotate when a run was bad and what the corrections were made in order to fix that. That's part of the annotations available in Panorama. Obviously, viewing the data longitudinally, a lot of these control charts and things that look exactly the same in Panorama for small molecules as they do for peptides. Oh, this was a really interesting example from Matt Rardin, who was at the Buck, and then Amgen. He showed this at the Skyline user meeting, I think just this past year. But this was just a really nice, where he basically took this contaminant database and downloaded them. And then we use this to screen our customer samples sometimes for contaminants. If they tell us, no, I did not put NP40 in my samples. And you're like, yeah, you did. You put NP40 in your proteins. I know your initial lysis buffer had NP40 in it. Because we can, look, we can set the document up, we can extract them, at the resolving power of the instrument. We have this contaminant database list, which Matt kindly provided. All we have to do is just go in and change the resolution of to match whatever mass spectrometer we might be using, and then extract the data. For Waters instruments, we now have the ability to do lock mass correction within Skyline as well. It was added a few years ago. And for small molecules as for others. And then you can look and say, okay, this was a known clean sample from the same set, and then this one, obviously not good. You've got all these peaks that correspond to the different polymers that we see. And so if you're looking asking why your database search results are low, or why you see some repeats in your data, it's very easy to have this document sitting on your desktop as a sort of just a document, the Skyline document that's sitting there. You can grab it and extract these molecules out of your proteomics data set, right, to see if you see contamination. It's a good thing to have handy. One of the biggest motivations personally to go to Skyline is the ability to take published methods and rapidly deploy published methods in our laboratory. So a lot of times they require multiple different chromatographic tools, and then manually entering examples. And so this is the data set which is used as part of one of the tutorials. It's a nice publication to get a lot of transition lists for energy metabolites, isotopes, and native. In general, the workflow is pretty simple. You have a published transition list, and you might need to do some minor reformatting to basically, for instance, this list has your heavy, your basically Q1, Q3 for light, and then Q1, Q3 for heavy. Basically, you need to copy these and duplicate them on the row below. It's kind of the reformatting that Skyline expects. Something like this, where you have a group of molecules, which is currently called molecule list name, which we might want to edit that to make it something a little more, but and then the precursor name, the label type, and then we have the precursor and the charge, product ion, charge, cone voltage if you've got that explicit collision energy. You can do collision energy prediction the same way for small molecules. If you have an equation where you want to just plug it in and do some sort of prediction. We found that it's actually much better if there's any literature values, that the values vary even between instruments. The optimal collision energy for a transition is very close between a SciEx machine and a Waters machine and an Agilent machine. They're not, for most compounds, they're pretty close. For some compounds they're fine, for whatever reason they're way different. But starting with the literature values, we find is more reliable than trying to predict based on any kind of mass of the metabolite. So you do a small amount of reformatting in Skyline, and then you have there's two ways to get data into Skyline now. The first way is to use this edit insert transition list, and you can format the table to match. But Brian, just in the last release, made something very nice, which is now, as long as the headers match what Skyline is expecting, you can just Control-C, Control-V, right, just like you would do a list of peptides in the left-hand pane, and it'll import all that information straight in. So that it's kind of like when you first learn how to do differentials in calculus. They teach you the long way, and then you teach the short way. This is, definitely the control page way. Control copy and paste is definitely the short way. The document tree you'll find, and Brendan showed a little bit of this earlier, is that the main things you'll notice is that the document tree is specific. So if you're just looking at a document and you're like not sure whether or not it's in small molecule mode or peptide mode, the little molecule here, you'll notice is kind of indicating that this is a small molecule document, right? We've got instead of a peptide list, we have now a small molecule target list. You can file export method, or you can file export transition list the exact same way that Brendan was showing yesterday in this. You can export methods of varying times, or you can schedule them. And you can also export positive or negative methods, but currently, and Brian, you can correct me if I'm wrong here, but currently I have not been able to export a mixed mode method, but maybe that only is a problem on Waters machines. I'm not sure. Our template, even if I put like a template that contains positive and negative data, I just have to export the positive method, export the negative method, and then just paste them together. But
yeah, I'm not sure about Waters, but if you're going to for some instruments, we analyze just fine, and actually we'll split them out into two separate lists.
Yeah, it gives you the option easily. You don't have to make two skyline documents. You just say export method, and it'll say positive or negative on positive ions or negative ions or both, right? So you can export either one.
Question back here.
Yeah, sure.
Yeah. How you are making this transition standard by using mass spec and getting to normal fragments? Are you using particle library or something like some software to make that?
All of the above. So in this example, it's basically this is a table that actually exists in a publication, and all I do is go and grab that list, put it in Excel, and paste it in there, and paste it in Skyline. If for something that's not published, you can either go from a small molecule library if you have built a small molecule library, or you can type it into Excel, record it into Excel manually. We do that a lot. If we've ordered a standard, for instance, and we're either infusing it, and we just measure the transitions. There's a lot of different choices for how you would gather that data.
This is like for small molecules, like only giving the first digit, like 239.2 and those. And if you're putting those here, transition list, and it's not matching with the accurate mass.
Yep.
It will show some error.
So that should be able to be, and I don't know if you covered it yet, but that you can use a method match tolerance. So first of all, if you've got a single decimal point for every triple quad out there, that should be good enough, right? If you've got an accurate mass measurement and you need to match accurate mass data to nominal mass data, then you do need to have an accurate mass library. So that's a generic problem because your library data wasn't collected under accurate mass conditions, right? So you do need to have in other words, it's not reciprocal. So if you've got accurate mass library data, that can be used to make accurate mass or nominal mass data for methods, right? If you've got nominal mass library data, you cannot use that to make an accurate mass transition line. You can't be more accurate than the data you've got to start off with. So a lot of people still, even if on the published databases for small molecules, a lot of them are triple quad, have been basically fragmented, and the data was collected on triple quads, right? So there's no way that you're going to have enough accuracy to then turn that into an Orbitrap PRM method, for instance, right? You'll have to set a wide wide window for mass isolation, because your Orbitrap ion will be in that window, right? And you can treat it like triple quad data, but you're wasting a lot of that instrument's power by doing that, right? You're going to introduce interference, right? So you can always lower the resolution of data. You can't ever increase the resolution of the data you have, in a very easy way. At least that's my interpretation. Brian, you add?
Yeah, increase accuracy. Even when you're developing an assay, you eventually want to go to a step down instead of. But if you have like a disk library thing that produces MSD format, we can read that. So if you've got high accuracy libraries, that's something sourceable.
Yep. And I would add that, one part of it that is easy to correct is if the precursor ion is always, even if it's reported as nominal mass, you can fix that, right? The fragment ions, a lot of times, are not annotated, so you don't know what the molecular formula of it is, right? MZ Cloud is actually a good resource now where they're starting to annotate molecular formulas for as many of the fragment ions as possible. So that is one. If I'm developing a new method, I tend to go to MZ Cloud. The disadvantage of it is that it's not automated. You can't query and say, give me the MSD file, for instance, for these 25 KEG IDs. That's really what I would like, where you paste in a bunch of KEG IDs and it gives you an MSD file, which is essentially your library for those compounds. That would be awesome. So that does not exist yet, I don't think, on any online tool currently. Other questions? Nobody's asleep yet. All right, we're successful for the first 45 minutes. All right. These are just for you to have as like reference points. So within each of the transition list settings, there's many times now a new tab, which a small molecule tab. So you've got a tab under the filter, which is specific to small molecules, looking at the precursor and fragment ion adducts. In small molecule land, instead of Y or B or C or Z, it's just simply P or F, so precursor or fragment. You have the library settings work the same here as you would for as far as the ion match tolerance, etc. Mass tolerances work the same as well. Edit import results works the same as proteomics as well. One of the features that I do use quite a bit is the ability to kind of nest, especially when I'm doing method development. If I've collected a positive ion and a negative ion data kind of subsequently, in order to have that data show up as in one sort of sample, I'll build a file tree which kind of has each of the data sets, each of those raw files in a folder that is named by the sample. And when you do that, you can add a multi-injection replicate in directories and then have two files in there. It'll import them as a single stick, kind of like Brendan was using earlier for all of the method development data. Retention time scheduling is quite easy, so you can import data with multiple method types and then export whichever one, you can then export a subsequent scheduled method based on whichever one of the individual data sets that you would like. So that's typically quite easy, part of the method development cycle. Additionally, collision energy optimization is enabled in the same way for small molecules as it is for peptides. So if you export a method that has a maximum number of transitions, it will tell you how many methods it's going to export, and then you can it will then repeat those same transitions but at different collision energies. A note of guidance for you that are doing small molecules. I typically do this in 2 steps for small molecules, so I'll do it. When you change the step size, I can show it to you in just a few minutes. I will start with 5 steps of like 3 or 4 volts. So it goes up 15 volts or more and then down 15 volts. And then wherever I find that maximum in that, I'll repeat it again with 5 steps of 1 volt. Right? So make sure I kind of get the right resolution around that one point. Because you can have pretty substantial changes in retention in ion intensity for small molecules within 3 or 4 volts of collision energy. Okay, so typically I will do that cycle twice for collision energy optimization for small molecules. Again, compared to infusing each compound individually and doing collision energy optimization, this is a huge throughput advantage, right? As long as you can measure, you've got reasonable, some reasonable estimate of what precursors and what products you should be looking at to start off with, this can save you a ton of time as you can optimize 30, 40, 50 compounds at once. And finally, calibration, which we're going to go to in just a few minutes, is a combination of a really nice interactive calibration curve viewer, the document grid, and then this viewing the peak area ratio to heavy. There's some viewing there where you can view the absolute intensity of the ion, of the molecule, of its heavy isotope, or the ratio kind of in one. This is another example where we can look at, sort of isotope incorporation. This example I'm going to show is just basically arginine has 2 different pathways to get to citrulline. One is through the urea cycle, and it incorporates, if you have, universally labeled arginine, so C6, C13-6 arginine and N15-4. Then you get 7 of those incorporated into citrulline this way, and this way you get 9. You get 9 out of 10 incorporated. So we can look at the ratio between these two. So Skyline gives us a nice way to, and this is an example of a CEMS run. So it's not just LCMS anymore. We got CEMS that Skyline enables, where we can look at a mixture of proteogenic amino acids in different matrices. This is a brain tissue extract. We can build a library of peaks. So that's one of the nice things. If you've got high resolution data and you've got a bunch of compounds that show up over and over and over again, one of the most frustrating things for high resolution data is doing database searching over and over and over again to try to identify these compounds. And for those of you who do this in small molecule world, there's no false discovery rate correction in small molecules, right? So there's no way to know whether or not you got it right or not, except for having the native standard. So once you run the native standard, you want to lose that information. And so what we do is we build a Skyline document that has all of those standards in it, and then we just extract that data out of our high resolution measurement each time, right, as the very first analysis step. You've got all those compounds, you don't need to worry about analyzing them anymore. And then you can move on with analyzing the rest of the compounds that are unknown, if you like. This is an example of how Skyline does a really nice job of taking advantage of the resolution settings. So this is, if you extract that 30,000 resolution in this case where the data was collected, we've got this interference, so we don't see a peak for this citrulline plus 9. But if we run the instrument at 120,000, when we tell Skyline we've run it at 120,000 resolution, it then extracts a much narrower window. We can clean up our extracted ion chromatogram. So Skyline is responsive in this way, of course, to the instrument settings, but you have to tell it. You tell it what instrument setting you collected the data at. This is something that is, as I understand, is ongoing right now. So there's a lot of development work ongoing here by Brian. I'd like to ask Brian to share a little bit about what's going on with library support. Admittedly, this is a feature I've not used a tremendous amount to this point in Skyline. So Brian, if you want to just share a couple of words about your vision and.
Sure. Well, it's analogous to what we've done on the peptide side. Say it's user driven. People have certain tools that are in their pipelines, certain kinds of search results, certain libraries they're using. We just want to hear about that, and we'll have support for it. So as you can see, we do support annotation of fragments. So you're right, the more libraries are coming out with annotated fragments and chemical formulas and things like that. And we'll pass that information through and display it. Yes, it's an ongoing project, and it's looking driven by what you guys need.
And concurrently, you will import anything that's in is it MSP format?
Yeah, so Started out with NIST because that's one of the more popular ones, and the transfer format there is MSP, which other libraries use as well. I have ambitions to get into things like HMDB and using more online resources the way we do with Uniprot on the peptide side. Haven't gotten to that yet.
Yeah, so ideas for small molecule, for libraries and things that, that's an active area where you can apply to the support, send a comment to the support board, ask for features, those kind of things. Okay, so all of this being said, this is all colored by the way that we do quantitative metabolomics in our group. So we focus heavily on, the sort of panels. It's a little bit differently than kind of how most labs we'll start with metabolomics. I will say that we started with metabolomics doing with what most other groups also start with, which is profiling. And after realizing how hard it is to just identify compounds for differential expression, and the numbers of clinicians that will come to me and be like, I got your perfect biomarker that differentiates test for control. And they're like, oh my God, I'm so excited. What is it? And they're like, I have no idea. I don't know. I'm trying to identify this compound. I have no idea what it is. That's frustrating. And so you then go to targeted panels and try to be as broad spectrum as we can. So currently, we have platforms in development that'll take us up over about 750. So we're making progress in that area. Okay. Resources for small molecule support. Clearly, the support page. Brendan and Brian are the key people here. Nick is the key person for calibration quantitation, which we're going to dive into right now. And then if you're desperate, you can contact me. I probably will not have the answer but I've got Brian on speed dial, so I'll just call him. But you're in all seriousness, you're welcome to contact me about any of the use cases. Importantly, the data that is collected for the tutorials was collected in our lab. So if you've got questions about the data sets or how those are done, you can contact me there. Maybe I can put them in the context or whatever if you're kind of working through that. Okay.
That's a great ordering you're seeing there. Though. If you start with the support board, you may already find your answer. And when you ask to the support board, that's got the advantage of the whole community being able to review that answer later. And more likely to get an answer faster because you suddenly have a pool of people to look at it instead of just one individual. And generally speaking, in fact, if you do contact us directly, we're just going to bounce you back to the support board for those reasons.
Yeah, and I'm doing the same thing. I would put things on the support board. People ask me questions, and I'll just put a question in the Q&A on there. So, okay. So what I'd like to do now is the most important part of this afternoon, I think, is to cover calibration in the context of small molecules. Okay, so we're going to do that. We're going to talk about calibration and quantitation. Do we need a 5 to 10 minute bio break to do that, or do we want to just keep charging through? I know there's not one on the schedule, but I don't want anybody's eyes to start floating. Okay, so I know we just had coffee. I'll tell you what, if you need a bio break, take it. I'll go slow for the first 5 minutes. I don't know. Okay, so what we're going to do, in order to get this material, you need to go to the participants page, and then under small molecule here, just right click and download. It's going to download this. Should come down pretty quick. Yeah. All right, so under downloads, where's Brendan been putting these once they're unzipped? Is there a specific spot? I don't want to dirty up his desktop or whatever. No. He's been just dragging them into documents. All right, I'm going to rename this small molecule.zip and then drag this into documents. I don't know, somewhere just under documents. Okay, you organize it how you want. I'm now in Brendan's documents folder. Okay, right click, I always use 7-zip. He doesn't use that. Yeah, 7-zip. Extract here. Okay, so you should have a folder, small molecule. It has two basic tutorials in it. We're going to open the first one, small molecule quant. Kind of look up when you got it. About 50% maybe. Getting there. Okay, I'm going to go ahead and open this first document. So if you just open, double-click transition lists, you'll see an example of, and under, this got 2 tabs, so I apologize that the default was the .grid tab, but open the TL tab. So this is a transition list, and in this case, anybody in here do pharmacokinetic measurements, PK? So we got 1. Okay, so this particular example is a kind of built around a pharmacokinetics, but it could be any small molecule. The idea is that we've got a drug, and then we've got an internal standard. Okay, now in the small molecule world, you may not have a stable isotope labeled version. It's not as easy to order those actually as it is for peptides. And just by any peptide, you can get synthesized small molecule version of it, or a synthesized version of it, pretty cheap. It just may not exist for this. And so what a lot of people do is they will use a surrogate internal standard, which may be an odd chain fatty acid for fatty acids. It may be something that closely elutes. In a drug context, it can be something like a chlorinated or fluorinated or an extra methyl group on the molecule, so it can be any other thing. So there's 2 examples here. I'm going to show you first how to do this with the normal way, which is just a stable isotope internal standard, okay? If we have time, then we'll go back and kind of show you how to do it with a surrogate. This is in the quantitative tutorial though, so if you find that there's a burning hole inside of you where the information on how to do a surrogate internal standard, well, it should be, you can go to that tutorial and it'll teach you that little piece of how to do it, okay? All right, so the first thing we're going to do, open Skyline. You don't have to use daily for this. 4.1 works just fine. Okay, and then go to open a blank document. Okay, I'll show you where the import function is. Okay, so if you go to Edit, Insert, Transition List. Sorry, his mouse has got a little bit more sensitive than mine. So if I look, I promise I've opened the software before. If I look like I'm, I have my oven mitts have to move around bigger area than his mouse is too sensitive. All right, and if there's a little radio button down at the bottom that just says small molecules. So now when you click small molecules, you'll notice there's a huge range of options for things. And if you then click columns, you'll see that some of them are enabled and some of them are not by default, and you can turn them on or off. Now, one of the really nice features, and I love how Brian, looking forward, if you have set up a library of compounds in here, he's built it so that you may have these identifiers from InchiKeys, CAS, HMDB, Smiles, etc., where if you then import a list of molecules using those identifiers, it would then be able to pull the information from the library for the precursor, product ions, all of those things. So that's built in kind of from the beginning, okay? That's not the context in which we're doing this tutorial, but that's built into the software from the get-go, all right? So what you would normally do, or what you would do in the old days, was you would check these things to basically make sure it matches your Excel file. You would, you might turn off a bunch of them and keep the adduct, and you turn off what you need to, okay, and then you, and I'm not clicking anything. You drag them to be in the same order, just showing you how to do this, okay? You don't have to follow along. Then you can paste in from your Excel file, okay? As you can imagine, people make mistakes doing that, right? It's a little bit of work to kind of get it to match up exactly right. So what Brian and his infinite wisdom enabled was the ability to go over here, and you just have to copy, just so highlight all of these fields, including the header. So important to include the header. You right click and copy, or Control C. And then over here, you can click up here and then Control V. Don't click there, just hit Control V. Okay. So if you expand this view now, you can edit, expand all precursors, and you'll see that we have a drug that has its molecular weight, its fragment. It's a deuterated internal standard, right? +3 internal standard, and it's product ion. All right, is everybody where we are? Everybody good? No? Where are we? What's the? Where are you having trouble? Oh, okay. Hold on. If you're having trouble, go to default settings. So go to settings, default. Okay, and then try pasting it again. Because what that means is that your instrument setting you had made some change to an instrument setting. Okay, everybody got that? So if you got a paste and it said you couldn't measure the fragment ion with the instrument setting, what that means is that you had set the mass tolerance, it was in your case, you had set the mass tolerance in your document to be, and what you were pasting was outside of the mass tolerance, okay? Everybody do this anyway. Go to settings and click default. Okay. Okay, now before we import our data, any questions so far? Everybody good? Yeah. Couple questions. Can you give me a first? Oh, yeah, just delete that. Yeah, so what happened is that you did the same thing I did the first time. You clicked on it and then pasted it, and it just pasted all the stuff like in the name of the file. So the second time it worked fine. Yep. Okay, so now before we import our data, we have to we want to check our transition settings. So I want to kind of go through what are currently called peptide settings and our transition settings. So you'll notice that the tool is still a little bit peptide centric, right? So peptide settings means molecule settings, right? And transition settings still means transition settings. But go to peptide settings and let's just kind of look through. So Brian said he's beating this thing with a hammer, and all these settings are going to just know. Is that what? Yeah. So some of these they don't have an equivalent in small molecules, and the tabs just shouldn't be there. For instance, digestion. There's no equivalent to digestion in the small molecule world. None of these things are there. It shouldn't matter. The single example may be we want to think about a background metabolome, but that doesn't really have an equivalent currently in the world of metabolomics. You go to prediction. This is currently not being actively utilized in a lot of labs, but there's no reason it can't be. So if you have a set of molecules which are retention time standards, especially like in a lipids kind of field where retention time can be based on the molecule polarity, pretty easy to kind of predict based on molecule class and polarity. This has a future. I don't believe that right now many of you will use this. I don't, but it is definitely something that can be used in the future for the small molecule pipeline. Again, this is something which I can't immediately off the top of my head think about why this has. Maybe a filter that uses some sort of mass filter that you already have in other areas would be useful. It doesn't really have an equivalent. Library, we don't have any libraries currently in here, but this is where your small molecule libraries would be as well. Modifications, again, we don't really have modifications, but what we do want to make sure we have is the internal standard type selected as heavy, okay, because we're using our stabilized tip label internal standard as our denominator in calculating our ratio. Finally, for quantification, we're going to leave these as none right now, but we're going to just take a look at this. So for regression fit, first of all, we can choose what type of fit we would like. There's a choice of linear through 0, so forcing the intercept through 0. I don't recommend that, but in some cases you might choose to do that if you've got very limited number of curves and the points and they're all kind of at the high end. Linear or quadratic. So there is the option for those. Now there's other fit types out there, sigmoidal, other things, but these are the ones that are enabled right now within Skyline. Normalization method, again, you can choose to equalize the medians, which just means that across all of the sample, let me make sure I get this right. So this is not something I've ever used, but maybe if I hover, it's got a help. No, it doesn't have a help. All right. So Mike, what does equalized medians mean? That's not something I've ever used, but I'm. Oh, okay. Yeah. So if
I see normalization,
yeah.
but many cases,
All right. So if but you wouldn't do that in the context of where you've got an internal standard. Typically, you would use the internal standard. You would do this instead of using an internal standard. If you, okay. Okay. Yeah. So you would not normally do a regression fit to a curve where you've got an internal standard and do this. This would be something you would do instead of this, quantitation that we're talking about. Okay. So typically it's going to be ratio to heavy. Okay. And then the regression weighting, there's sort of 3 common ways. Either when you're doing a logistic regression to a curve, you can either do sort of standard weighting. You can 1 over x or 1 over x squared, which just means that you're weighting the bottom end of the curve more in order to get a better fit at the bottom end of the curve. We will typically look at the nice thing about Skyline is you can change these fits on the fly and then look at the residuals or the bias at the bottom end of the curve and see which one gives you kind of the best fit to the bottom of the curve, okay, for each peptide. One thing that's not currently enabled is to choose a different regression weighting or regression fit for every molecule in your document. Okay, that's not something that, in other words, you may have molecules that you calibrate that it's less common to have some fit quadratic and some fit linear, but it may be that you'd rather use a 1 over x for some and a 1 over x squared for another. Currently, it's document centered, right? So you select the fit. And what we've done is we've just broken out, if we have a set of molecules that are from the same assay that calibrate better one way than others, we just make 2 documents. One which is a 1 over x set and one is 1 over x squared set. All right. And then the MS level is either MS1 or MS2 or all, right? So if you have the potential for DIA data, for instance, where you've got MS1 precursor intensity and product ions present, and you've got extracted ions for both, it can use both intensities or one or the other, and with a click of a button. You can choose to calibrate based on product ions or on precursor or on both, right? In this experiment, we're using all because it's just an SRM experiment. Any SRM experiment is going to be 2, right, or all. It's going to be the same. Okay, and then the units allows us to set the units of our calibration curve. Okay, so we're going to revisit this we're going to close this now without making many changes. Okay, the changes you make, if you have made some changes, that's fine. Doesn't hurt anything. We're going to come back to this in a few minutes once we import some data. Okay. Now we need to set our instrument settings. So go to peptides, or go to settings, transition settings. Start with the prediction tab. So by default, we leave the precursor mass and product ion masses to monoisotopic. If you drop down under collision energy, you'll notice a bunch of different settings for each instrument. Okay, just click on water Zevo right now, and then click on edit current. Okay. So what this does is for peptides, okay, it brings up the slope and the intercept for charge state 2 and charge state 3, okay? And then it gives you some information here is if you're going to manually deviate from this using a collision energy optimization, so if you're going to actually run a collision energy optimization experiment, how do I do that, okay? Remember when I said we're going to start off with stepping wider and then go to a narrower step, okay? So what I'd like you to do is cancel out of this, okay? Go and say add, type in small molecules, one, a slope of 0, and an intercept of 15. Okay. So what is this going to do? Anybody think about what is this going to actually do in the small molecule context?
Every small molecule will be measured collision energy 15.
Yes, that's exactly right. So if you have a small molecule that does not have a defined collision energy, right, the default will be 15 volts. Okay, you can choose this default to be anything you want, but 15 to 20 volts is probably a pretty good starting point for it. You don't know anything about this compound, right? You just want to measure, what the intensities do. What I would do then is I'd change the step size to 3 and the step count to 5, right? It should be already at 5. So what this means is it's going to go from 20 to 35. Right? And then it's also going to go from 20 down to 5, right? So it's going to span 5 volts to 35 volts, right? Within the first experiment you do for collision energy optimization, okay? Again, typically what you're going to do is you're going to import a list which has already defined collision energy from some literature source, right? Either above be from an online library or from your own kind of manual, optimization, or you're pulling it from a publication. You'll have some starting point. The top part here will not override what you put in your collision in your explicit collision energy. Okay. So remember in this we have explicit collision energy set to 16. Okay. So anything in this settings tab does not override that explicit collision energy. It's the opposite. If you put something in the explicit collision energy, that automatically overrides what is in the settings, okay, for the prediction settings. But it still uses this information to do optimization. So if you have 20 or 16 put in for your explicit collision energy, it's going to start there for your optimization and still go up and down by steps of 3, count of 5. Does that make sense? Is everybody following me? Who's not following me? Anybody? Okay. So this allows you to basically set a single setting here that will handle both molecules that don't have any known collision energy information, and will also change that setting appropriately for when you do and you want to then you want to do optimization. What I've even done is I've got 2 settings in here. One that says small molecule OPT1, and then the second one which just says small molecule OPT2. So the optimization 1 has these settings as I've gone here, and then optimization 2 has a step size of 1. Right, where I start off with a wide optimization, and then my second round I just come in with a narrow optimization. Okay. All right. So let's click OK. So now in your when you go home, whether you like to or not, you've got small molecules in your window there. You'll look at it and hate me every time until you decide to delete it. All right. There are other instrument-specific criteria, declustering. Optimization libraries are not currently enabled. That does not have functionality yet, correct? Awesome. Again, compensation voltage isn't also a SIX specific. If you then click the use optimization values when present, you have an option here to then optimize on the precursor level or the transition level. Okay, so if you use the optimization, if you're doing a collision energy optimization experiment, it's really important to click this button, right? Because then when you export the next method, you don't want to use the original values, you want to use the new best values, okay? And if you have precursor highlighted, it will use the optimum at the precursor level. If you have transition optima highlighted, it will pick the best collision energy for each individual transition at the transition level, which is important for small molecules. Next tab, filter. You'll notice that we've got this nice, handy small molecule tab. So the important thing here is we're doing a positive ion, so we want to choose M plus H. We have M plus fragment, but if you click the expansor, you'll see that there are an expansive list of potential adducts that you can add to your molecule. So if you paste in a molecular formula and you want to then expand the number of adducts that are used, you can highlight these and just keep adding, particularly in the context of lipids where you may have an M plus H, an M plus ammonium, an M minus water, an M plus sodium, and you want to track them all, you just select them. Okay, it will track them all. If you now go to, ion types here, if we're doing fragment ions, so we can just keep F, but if you have a precursor, you can add a comma P here. It's just would be as simple as that. Okay. Library. So currently we're not, you can uncheck the library spectrum available, but eventually, or if you're using a library, you would be able to pick how many ions out of that library did you want to use, how many product ions that you wanted to use, and the match tolerance between your library and what your data is. Under instrument, this is one of the sort of the most critical settings for the purposes of small molecules. If you're importing data that has a lot of times for small molecules, you have several compounds with very close masses, if you're doing triple quad even. And so you can actually play a game here where if you have 2 molecules or 3 that have nominally the same mass, you can set the method and the match tolerance tighter than the actual masses. So if I set it to this to 0.01, right? I've got then a molecule and its geometric isomer that are the same mass and the same fragment ion mass, but they migrate at different times, right? And what I can do is I can set the target mass to be 0.01 different between the two, which is going to make absolutely no difference in the way the data is acquired, right? And then you can set this to match the tolerance that you set your data to, right? So you can that makes it, that combined with retention time, explicit retention time, makes it so that the software doesn't make mistakes on integration and which one, picking which molecule is which, right? So you can use this to your advantage. For now, let's set that to 0.02. And then under full scan, we're not doing any full scan, but if you were, you can, there's going to be information later in the week, which you can then think back about small molecule world, and it applies the same way. So if you're doing high resolution metabolomics, you can go down, you can set either to the % of the base peak intensity or the count, look at the number of peaks. You can choose then, okay, what kind of analyzer or either a centroid mass selection. So we're not doing that in this, but that is included in the high resolution tutorial, kind of the settings and how to do that. Okay, That's a lot of information on settings. So any questions on peptide or precursor settings or transition settings? Yeah. Uh-huh. Yep.
You understand?
Yep.
You are right with that.
Yep.
And they have to do the religion.
Yep.
When you're analyzing using the skyline.
Yep. How do you make it pick the right one?
Right.
How do you make it pick the right one?
Yes.
Yeah.
So it's always picking which is first. This I have the SQL MRA. So it's not extracting the data for the second week. It's extracting only the first week.
Even if you put an explicit retention time in there. Have you used explicit retention time?
Yes.
I'm sure Brian would love to see that example. Yeah, because typically if you have explicit retention time in there, it will heavily weight the integration towards that retention time. And so it will bypass that first peak, particularly if they don't share the same window. Like, is this high resolution data? So this is this triple quad data. Yeah. So particularly if they share the same transitions, but they have a window, you know, they don't. The only time I've seen this is where they share the same transition window space. In other words, they're not separated very much. Yeah, no, they should not make that mistake. That's something that Brian would love to see, I'm sure.
That's why we have chromatography, right? So that is surprising.
Yeah.
Also, put in a word for ion mobility, which is another separation dimension that can be used with this stuff in sunlight.
Yep.
Although a lot of people don't have that information.
Yeah, but it's also in the high-res world almost exclusively. There's some triple quad stuff talking about for differential mobility, but strict ion mobility, pure ion mobility is almost exclusively on high-resolution instruments. So, but that can be added, can be used. And so these guys have done a really nice job of including as much sort of identifiable information as you have about your molecule. You can use it to make sure that it's selecting the right peak. I mean, it's what Mike was talking about earlier. I mean, like a priori knowledge, like knowledge that you have ahead of time. You want to use all that knowledge that you can, right? And retention time, it should be using that heavily. It should not make that mistake. And that's going to be the exception, should be the exception rather than the rule at this point. Yeah.
Just out of curiosity, so cases like liquid fragmentation, where you use both the positive and the negative fragment ions to identify the limits. For example, for the phosphated alcohol, you want like 184 in the positive.
You want the chains and the negatives, right? Yeah, absolutely, absolutely.
So, what do you do here to integrate both?
Yeah, so that is something that I don't think any software package really does well yet that I've seen, and would be super cool to do. So, are you doing that? Are you typically collecting this in switching mode, or are you collecting it one run in one mode and another run in another mode?
So this is my past story.
Yeah.
I used to do it in switching mode.
Yeah.
We do support that.
Yeah, you should absolutely be able to do that, because within one precursor ion, you can do adducts in positive and negative, and then
Just declare the molecule as having, let's say, N plus H and a minus H adducts, and I like one.
yeah. I'm not saying anybody do it yet, though. Has anybody?
Some examples.
Oh, good.
Including
Good.
Switching. But also, if it is two separate runs for different polarities, we'll deal with that as well.
You can dump those both into one file for the sample and then import them effectively as one run, right? Is that the way you would deal with that? Like if you've done a positive mode run or a negative mode run and you want it to be one sample, you can put them both in the same directory and import it that
I'm
way?
not sure, actually. Now that you say that out loud, that would be important.
The precursor mass will be different here for the positive and the negative mode.
Yeah, but you define, so the way you do this is so under the adducts, so you give it the molecular formula for the neutral molecule, right? And then you tell it M plus H is.
So this is the neutral mass, not the adduct.
No. For this, so there's a couple. Yeah, and I glanced over this. So for this example that I'm showing, we're pasting in just masses, right? I'm saying that I've observed that this molecule, I'm calling drug X, shows up at this mass to charge and that, right? That mass to charge for product. Skyline is very smart in that it allows you under. So I'm going to hit OK here. If I go to Edit, Insert, Transition List, I have the ability to, under the precursor formula, this is typically, and let me just remove a bunch of these so you can see this. And this is covered in the high-res tutorial. But if I give it a precursor formula and an adduct, the precursor formula is actually the neutral mass, the neutral molecular formula of the compound. And then the adduct, and Brian deserves a lot of credit for coming up with the way to handle this. But so the adduct then tells you can take that neutral formula and say, okay, it might be that precursor formula is seen 4 different ways. It's seen M plus H and M plus ammonia in positive, and M minus H in negative, right? They all have the same precursor name. They've all got the same precursor formula, and they're just different on the precursor adduct, right? And then if you put the charge in there, and then hit check for errors at the bottom, it will then calculate the precursor MZ for all of them, right? And those will be the ones that it'll look for at high resolution, right? Oh, necessary anymore. Okay. So it'll support that. And if you have fragment ions under each one of those, then you have a different line for each fragment ion as well. The way that the data is. So. Great question. Thanks for letting me think through that, and Brian for saying, no, we do that. Yeah. Other questions? All right, let's import some data. First thing you got to do is save the file. So File, Save As, and then under, I'm just going to go wherever the root flow. The best place to do this is under the root document. So under small molecules, single molecule quant, just call it SM_quant. Save. Okay, so now we're going to file import results. You can import several or many at once. Go into this 96 well data. Don't import it all yet. Kind of expand this view. I want you to import run 80 through the end. All right, so what we have here is some unknowns, so 80 through 96. We've got blanks, calibrators 1 through 7, so we have a 7-point calibration curve, plus the blank. We have a double blank. You might know what the difference between a blank and a double blank is? Both come in the context of all calibration. So a double blank is a sample which does not contain any internal standard or any analyte. Okay? A blank contains the internal standard, but no analyte. It's blank for the analyte, right? But you use it, the ratio of the blank to the internal standard can calculate something about your limit of detection, right? Because it's got the internal standard in there, it can be used to calculate. So double blank is just experimental, just chemical noise, right? The background. All right. So that's the difference between a blank and a double blank. And then quality controls, low, mid, and high, each run in triplicate, and then our study pool QCs. Okay. So we're gonna click OK, and it's gonna import all of those runs. All right. So when it's done, you can look up. Should be finished. So now, in order to get a kind of an overview of our data, let's view our retention time and our peak area. So view retention times replicate comparison. Okay, kind of put that up at the top. then view peak areas, replicate comparison, put that somewhere as well at the top. Okay, so now you'll notice that when you click on the light precursor, it just shows you the light intensity all the way across, the native intensity. And we've got some variability in our samples. We've then got what looks like a calibration curve. It looks like high, our double, one of our double blank here, our high, low, mid, and then our study pool. Okay. If we click on the heavy isotope, anybody notice something funny when I click on our stable isotope internal standard? Anybody notice anything weird about this that Skyline kind of helped us to pick out really quickly? Everything look great? No issues here? Look at the intensity of our internal standard. If we've prepared everything the same, what should happen with our internal standard? If every sample was prepared equivalently. Remember what our internal standard is? You spike it into each sample, then you prepare it the same way all the way through your protocol, right? So in this case, for whatever reason, we've got our stable isotope label internal standard and our unknowns. Then we've got our stable isotope label internal standard in our calibration curve, and then in our quality controls and our study pools look like our samples. So this is an indication, this is one of the things that Skyline does very nicely. One of the first things you should do in a quantitative experiment is look at the intensity of your stable isotope label internal standard across this experiment, all the way across. Is it the same, right? Across all. Now it shouldn't be in the double blank, of course, right? But this tells you that you've got some sort of matrix effect whereby the matrix, being the background that you're using to calibrate in, causes me to get a lower response for the internal standard than I do in my sample. It may or may not be an issue, and what's going to tell me whether or not it is an issue is whether or not I calculate correctly the amount in my quality controls, right? But this will be something called like an inverse matrix effect. So in this case, we've got something in our samples that are quality controls that's helping my analyte to ionize better, right? It's helping my internal standard. We know that because this should be completely flat all the way across, okay? I point that out not to blow holes in my assay here, but to point out that how easy Skyline makes it to look at the quantitative metric, the first thing you should look at, right? Which is, are my internal standards integrated the same across all the samples? Okay, so now the next thing we need to do is, currently Skyline does not know which samples are what, right? Just looking at these, they're all, it doesn't have any knowledge of which ones are analytes, which ones are samples, which ones are calibration curve. Okay, so if we do something where we go to view calibration curve, it's plotting them, but it doesn't know that it's plotting them all as unknowns. Okay, it doesn't know what's the calibration curve and what's not. All right, so what we want to do is go to our document grid. So view document grid. And in the document grid, we have this ability to view replicates. So we have the sample type is the first important thing here. So if we scroll down, we can annotate each of these as the type of sample they are. So if you look at the drop down, we have a bunch of choices. So you can drop down, click blank, or you can just click highlight and hit B blank, right? And then standard, right? Or once you've entered one, you can highlight that, drag down across all your standards, right click, and say fill down, and it will fill down all to the point that you say. All right, so I know I just did a lot of stuff there, but you wanna leave the top set as unknowns. You wanna set these blanks to blanks. You wanna set the calibrators as standards. Double blank should be a what? Double blank. And then QCs should be quality control, because it understands it's doing the calculation, right, whether or not you got it right. So again, quality control. Now the only exception to what may seem logical here, so we're going to drag this down, right click, fill down, is that we're going to leave our study pool QCs as unknowns, because we don't, the difference between those and an actual QC is that we don't know what the number should be for the study pool QC. It's a true unknown, right? We know it should be in the middle of all of our samples, but we don't know what that number should be. Right? We do for the low, mid, and high QCs. Those are known unknowns. We know what the value should be, so we're able to type in a number on the right in the analyte concentration, right? As to what this is. Okay? Has everybody managed to fill in this document grid so far? Where we are. We're getting really close to seeing a calibration curve here. No, everybody's excited. Okay. The next thing we need to do in order to build a curve is to give it the values, right, that it's going to use to plot these calibrators and quality controls. Okay, and you can type them in individually, but the best way is to go to this document grid. You'll probably have something like this in your kind of experimental setup, where you said, okay, the sample I'm going to call this has got this calibration range, right? All right, so what you need to do is highlight this column, column C. Don't get the column header in this case, just get column C from B2 down to the end. Control C. Then go to the top, right click, click here, click here, highlight it, and paste it. Control V. You want to double check that it makes sense. So as you go down, you should see that the standards Cal1 starts with 10, 20, 100, 200, all the way up to 800. So give it a manual kind of sanity check here. All right, everybody's looking up, so I will, you guys following along? Yeah, good? Yeah. So go to views, you choose replicates. Yeah, so the replicates views, yeah, there's a bunch of different views in there. Yep. Yeah, if you don't see a screen that looks like this in your document grid, then chances are there's, the document grid is a tremendously powerful and yet very complex world. So you can get lost in the document grid pretty easily if you're not careful. So just be sure you have this. The difference between these sections of the document grid is that these top 5 are not editable. You can't edit what shows up in these. You can use these as templates for other things. These are editable. Okay? And you can use these to add new ones or whatever. They will always show up down here. Okay? But this is, I think, I don't know what the history is behind that, but in my mind, it's a way to at least keep you from completely getting away from anything that resembles reality, right? You can always go back to one of those and it's like it should be. Okay, and a couple people that were kind of catching up, but everybody good? Okay, good now? Did you get mostly caught up? Yep, awesome.
One other thing that's cool about the document grid is that most stuff you see in there is talking about what's in your document. It's not view only. A lot of it you can actually go in and just edit right there.
Yeah.
It is quite powerful. It's also fully customizable, so yeah, you can get totally lost.
Yeah. And I think there is included, and there's more about how to customize it in some of the tutorials. We're going to modify one of the views a little bit in just a second. Okay, so now we have this ability. One thing I want to do to so let's go ahead and view our calibration curve. So go to view again, view calibration curve. So you'll see that now it's still giving us an error. It's not really giving us a fit at all. And that's because we haven't told it, remember, what kind of fit to use, okay? So if we go back into peptide settings, you go to the quantification tab, we now want to tell it to go linear, ratio to heavy, and let's start with a 1 over x squared. And let's type in some, now this is just a text field. This is not going to do anything to your data. These units, it just makes it so that the units along the bottom of this show up as a concentration. Okay, it's just a text field. So don't worry about what this is doing, multiplying to your data. Just make sure that whatever units you want your data to be reported in are the units that are down here. So now click OK. All right. So now let's take a look at our calibration curve. What do you guys see? What do you guys see here? What's good, bad, ugly? Do I like anything or don't like anything about this calibration curve? What are the figures of merit that we look at when we look at calibration? I know you guys most of you guys probably don't do this much anymore. Maybe you did in undergrad analytical chemistry lab. R squared is our goodness of fit, right? What do we think about a 0.97? It's all right. It's not great. Why is it not great for this curve right out of the box? What do you see that may be causing it to be not great?
Your standards is the
Yeah, one of the standards looks visually like it is pretty far off, right? This group here is kind of out of Cal 5. It's pretty far out of calibration. Now we can go in, we can right click on this and exclude it, and both of them. We can zoom. This is interactive, so we can zoom, we can right click, we can exclude it if we wanted to. But I want to caution you away from kind of doing that empirically for now. So we zoom back out. Skyline does a really, also in the document grid, you can calculate. So what we're trying to do is set rules around this, right? So we want to exclude standards which are, say, outside of 15% from the regression value. And we allow ourselves, to exclude one standard out of a curve, right? In order and still maintain the fit, right? Maintain a goodness of fit. So we can go in and view. The question is, what is the actual bias calculated here? What's the accuracy, right? If we wanted to back calculate through the curve, what is the accuracy here? So in order to show that accuracy, if we can go back to our document grid, so view, document grid. And I want to go to the peptide quantification view. I'm sorry, not peptide quantification. I've got this set up in my document. This is the danger of not doing it on your own computer. These look a little different. Oh, I'm sorry. So peptide ratio results is the one you want to start with. So view peptide ratio results. Okay, now this is obviously not a peptide. Okay, so what we want to do is customize this a little bit to show the things we want to show. All right, so go to views, edit view, call this molecule with accuracy. All right. Now we don't need to include the peptide sequence. We don't need to include the protein name. We do want to use the search function here. Find precursor. And if you do that, if you find precursor, it's going to bring up a bunch of other things. So we want to basically show the molecule name, right? And put that first. Replicate name. We want to include the So let's type in accuracy, hit find. So when we type in accuracy, it opens this quantification tab, and this is what Brian was saying about this being tremendously customizable, because you've got a tremendous amount of things that you can show here. I prefer to view the calculated concentration and the accuracy, right? And then you can type in exclude. Is that the name for it? Include. What's the word that what's the term you use, Brian, for whether or not to include a point in a calibration curve? It's called, let's see if I can find it. Exclude. Oh yeah, it was exclude. I don't know why it didn't find it. I thought it was exclude. It is right here. Exclude from calibration. So click on that, exclude from calibration. All right, so now let's kind of reorder these. Let's put the accuracy down at the bottom. Let's put the exclude from calibration last. We can exclude the peptide peak found ratio and the peptide retention time. Okay, click OK. So now what we have is for every replicate, we have a calculated quantification. We have an accuracy only for those which we defined the concentration before. Okay, so now you can look and you can say an accuracy of 100% means it was exactly on the line. Okay. As you go down, if we're looking for an outlier, a cutoff of 15%, we can see that these 2 points are far outside of 15. They're like 26%. So we have a couple of options with how to exclude them. So I want to try to view my calibration curve and the document grid at the same time. So I'm going to move this over here. And I'm going to drag my calibration curve out here. So if I right click and exclude the standard, you'll see that it updates all the calibrated values, and then it also puts a checkbox here, right? You can also just check the checkbox, exclude, and then once you hit enter, it will remove that completely from the curve. So now you can look at a couple things. So now our R squared is 0.99, and we're back calculating also, if you had noticed before, our quality controls, we're back calculating them, much more accurately. Interestingly, we still are off by, almost the margin of our margin of interest here in the middle. This particular point here, you also might want the high point on the calibration curve. You've got one that's 90%. That, by our standards, would not be excluded. But that's you can, if you think your goodness of fit for your QCs is going to improve, you could consider excluding that 1 point. A couple of other views that are interesting. So this gives you our light to heavy peak area ratio. You can notice that all of our standards all of our analytes currently are kind of in the bottom of the calibration range, but they're all between calibration 2 and 3. So we're definitely in the linear range. So I encourage you to kind of interpret your calibration data first using a limited number of unknowns from the sample set, and just your quality controls and your calibration data, because it's just less busy. But now, since we've looked at our curve fit, our quality controls are within tolerance, now we're going to go ahead and import the rest of our unknowns, okay, into this data set. So let's go. We're gonna save this again. Just hit save, and then file, import results. We're going to go back in and now import run 4 through 79, the ones that we didn't import before, and hit open. And you'll see as those are imported, they're added to the document grid and they're added to our unknown. So these are continually being populated as the data is being imported. Updates in real time. Okay. I find that after this is, particularly for a situation where you have a small number of analytes, that this table makes a pretty good point to go ahead and export this document grid that contains the ratio to the standard, the sample name, the replicate name, and the accuracy, the concentration and the accuracy makes a good point to go ahead and save the data, export the data for a report. So with that, it's just as simple as clicking the copy button and you can paste it directly into Excel. So this copies the entire table. You can paste it directly into Excel. Other thing you might notice is that you can click on any one of these points here, and the whole thing is interactive. So it'll update. It'll bring up that particular raw data file. So if you have a question around the analyte internal standard for a particular analyte, or a particular run, you can click on that run and it'll bring up the raw data. If you have, since we're getting near closing, since you have a question about, if you have a question about integration values, you can, or boundaries, you can click and drag and then apply those. Notice a couple of things. One is the very beginning of kind of an audit trail, where if you reintegrate a peak, it will color that peak. You can choose not to show that, so you can choose not to show the original peak, but Skyline has now recorded that you manually reintegrated that peak. Okay, and that's recorded into it. So we have questions like at Merck, we did a course of like what's kind of restricting the use of Skyline in a regulated environment, and mainly the thing is an audit trail. I know that's an active project within the Skyline group here now to develop that. Okay, I'd like to give the last 5 minutes for questions about calibration in general, how you might do it. There are now, if you look in the daily version, you'll find that there are settings for establishing the LOD and the LOQ. And so under calibration, under quantitation, there's a new kind of section down here. And you get the choice on how to establish, and Lindsay's going to talk more about establishing the limits of detection and quantitation tomorrow. So that will make more sense. You can reanalyze this data set it's a fairly simple data set, so you can reanalyze it in the daily very quickly. Once you've done it once, in order to test this, you run through this. Now that we spent an hour doing it, you can run through the reanalysis of this data set in 3 minutes. It's very, very fast. And use it to kind of test limits of detection, kind of different algorithms for doing that. But quantitation is exactly the same for an individual peptide as we talked about here. Other questions?